All right, thank you guys. Thank you so much for having us. We wanted to maybe talk about this on a slightly different angle. We just wanted to cover, how we can actually leverage industrialized construction to do things maybe a little bit differently. Maybe we can be a little more efficient with our materials. Maybe we can be a little more sustainable with our building. So a little bit about that, and then Blake's going to talk about our new building system that we've been developing and rolling out in the market. So. Just real quick, Blake and I are both from Clark Pacific. We've been doing industrialized construction, although we called it precast back in the day, for 50, almost 60 years now. So locally, we did Escondido Village. A picture right there is Stanford. That was about a 2,000 square foot student housing project that was completed.
2 million.
What's that?
2 million.
Oh, 2 million, I'm sorry, 2 million. Had a 2 in it. We're both engineers, right? So we don't do good with numbers. I'm a product manager, so senior product manager with Clark Pacific. So I'm developing building systems like the one that we're going to be presenting, and I'll let Blake introduce himself.
Yeah, and we're both structural engineers by background. I'm a development manager for Clark Pacific with our office and our lab building systems. Working with Jon in product development, but also in educating the marketplace and helping our customers understand the benefits of prefabrication and how it can add value to their projects.
All right, so real quick, I know you guys have all seen this. Building industry has a carbon issue. So built environment is responsible for 38% of the world's carbon emissions. 10% of that is a direct result of constructions, the embodied carbon and all the things that we build, right? So where do we start? We need to really truly understand where this carbon's coming from. So the first thing you should do with everything that you're building is kind of break it down at a high level. Just where is it? Where's the carbon? Where is it going, right? And so for us, we're responsible for the structural system and the facade systems. So we can break our system apart, and we can start looking at all the different parts and pieces and components that we build with. And we can say, like, this is a typical building for us, right? So where's the carbon? Okay, I look at it as in where's the concrete for us, right? Because concrete has a fairly large carbon footprint. So I look and I say, okay, the floor system has a lot of carbon, and the foundation system has a lot of carbon. So if you're going to tackle this problem, you need to start where you're going to get the most bang for your buck, right? And so you focus on those big items, like say tier 1, and then say tier 2 is like you go down to the beams and you go down to the shear walls and things like that. So understanding where those are helps you understand where to focus your attention. I listened to a guy talk for an hour on optimizing the carbon footprint of a column. And I look at my columns and I go, I don't really care about the columns, right? They're like an insignificant part of the building for me. So just make sure you're putting your effort where it's going to pay off, right? So before we can kind of look forward into how we can change things, right, we need to kind of step back and take a step back and look at where we've been. And, one of the things I forgot to mention on that other one is, let me back up here. Sorry. One of the things we've done, really focused on at Clark Pacific, is we've really focused on our mixed designs. So I mentioned that Portland cement's the main binder in concrete. That is responsible for about 90% of the carbon in concrete. So when you say, I need green concrete, what you really need to do is get rid of the Portland cement, right? The challenge with that is you replace it with things like supplementary cementitious materials, which are like slag, fly ash, basically industrial waste products. You put those into the concrete, and you're taking the engine out, right? You slow down the chemical reaction when you do that. So all of a sudden, these things that they're building out in the field take a lot longer to cure, and the whole process just slows down, right? So we have been working on mixes, and we've also been working on production methods that allow us to accelerate that mix and allow us to use anywhere from 25 to 70% replacement of Portland cement in our plant. And we call this, we've just rolled this out, we're calling it our Carbon Shield product line of cement mixes that we're putting into our products. So didn't want to forget that. So So before we can move forward, right, we need to think about, okay, where have we been? And I always like to start with cast in place because everybody likes to pick on cast in place because we've been doing it for years and it uses a lot of concrete, right? So why do we build this way? I mean, you look at this and you go, okay, everybody builds with a two-way flat plate, right? This is a very, very common construction method in the United States. But as an engineer, it doesn't make any sense to me, right? The shape, why would we build a flat rectangle that's going to sag, right? That doesn't make any sense. It's not efficient. So why do we build that way? We build that way because, well, it's not efficient for materials. It's very efficient for labor, right? The formwork is flat. The labor is very simple. You're just laying rebar down in rows. It goes very quickly, right? So in a sense, we're trading the material for labor, right? And that's kind of an analogy for what we do out in the field every day. We're constantly being inefficient with material so we can be efficient with labor, right? So, and it's getting worse, right? I know this has been up, I've seen this in many presentations, right? But I love it. It's the McKinsey study on productivity and talking about manufacturing productivity versus construction productivity and how manufacturing productivity keeps getting better and how we keep getting less productive out in the field. Right, so we keep finding ways, more and more reasons to trade material for labor by doing this, right? Okay, so what does that mean, right? So if we're going to off-site fabricate, we simply don't want to replicate what they're doing out in the field. We need to do it a little bit differently, right? For us, labor is going to be easy, right? Give it to us. Give us all the labor we can because we're going to find a way to take that big amount of labor and squeeze it down into a little tiny bit, right? So we don't necessarily want to optimize the same way they optimize out in the field. We want to optimize different, right? So what I mean by that, like, okay, so here's a typical wide flange beam, right? Steel system. I'm going to pick on steel now because I like to pick on everything. Equal opportunity, all right? So we've been doing this the same way since people were sitting on beams without shirts, right? So why do we, again, let's look at this. So we build a steel beam, we put metal deck on it, we pour concrete over it. Composite action, we get a very strong, stiff system, right? But in the end, a lot of that stuff's not there it's not needed in the end, right? Like the metal deck, what is that there? It's just there to hold the concrete in place while the concrete cures. I mean, it does a little bit more than that, but in a sense, you don't really need it, right? So, and in a sense, you don't need the flange on the top flange. You could just get rid of that. That's material that's not needed in the end system. But it is needed during the construction, right? And by that token, you don't need the metal deck. You could get rid of that too, right? So there's all these things that if you're manufacturing off-site, you can take advantage of things that you can't take advantage of out in the field because you can manufacture it into it. So just always be thinking about that when you're coming up with your new construction techniques and your new technologies. Always don't go, okay, I'm going to deliver exactly the same thing but different. No, deliver something different and different, right? So here's our solution, right? So here's the floor panel that we developed. You notice it's very different from the cast-in-place two-way flat plate. It's got shape to it. It's got ribs, right? Those ribs give it strength and stiffness and allow us to use a lot less concrete for the same strength and stiffness of the system, right? So we have this is the floor system, right? I identified earlier this is like 35% of our building. So this is something we really want to get right? So we set some goals. We say, okay, on this system, we want to do 70% cement replacement. In a sense, we're going to take a whole lot of carbon out of the structure. Okay? We need, for our manufacturing performance or for the way codes are written, it's a whole different thing, right? We need 3,500 PSI overnight so that we can strip this, take it out of the form, and put it into storage, right? We also want to reduce our concrete volume by 25%. So again, I did that by changing the shape. Notice it's got a really thin slab, right? It looks a lot like steel construction. So the slabs are, just being greedy, right? We wanted to make our slabs thinner than concrete over metal deck, just so we could say we did it. So we're using very, very thin slabs, right? So we set a bunch of initiatives. Okay, we want to leverage the shape to reduce concrete volume. We're using pre-top system. Again, most concrete, precast concrete, you put the concrete down, then they come over it and they pour like a 3.5, 4-inch topping slab over it. That's a huge waste of concrete, right? You're using way more concrete than you need because you're putting it in there. You're basically creating a concrete structure to hold up another structure. So by getting rid of that, we're able to save a lot of volume. And then By doing our own UL testing on this system, the code says you need 5 inches of concrete in order to meet UL. We only needed 4.5 to meet the capacity of the system. So we tweaked our concrete mix, went out and got our own testing for UL so we could supply a 4.5-inch concrete system. So we eliminated a 1/2 inch of concrete all the way across. So that helps weight, it helps cost, it helps the environment, right? So these are some of the things. And then heated forms, that's the key to us providing that 70% replacement. We actually heat our forms. The temperature that goes into the forms, maybe it adds 6 to 8 kilograms of CO2 per yard. It removes like 100. So it's a win, right? So that's kind of how we're approaching it. So with that, I'm going to hand it off to Blake, and he's going to talk about the rest of the system.
Thanks, John. So I'm going to talk about how we took those principles that John just spoke about and turned them into this product. The net zero building platform is the culmination of years of design and construction of unique buildings that we've done at Clark Pacific, where instead of delivering unique buildings each time, where you have different designs with different components and different ways of doing things, we've productized that effort into a single integrated prefabricated commercial office building solution. This solution combines 3 building systems into a single integrated product. Those 3 systems include the structure, the mechanical system, and the building envelope, or the skin. And the focus and the priority of doing this is sustainability. We're taking a holistic view of sustainability of the building by looking at embodied carbon and operational carbon and end of life, which are all things that you have to take into consideration. John spoke about the embodied carbon quite a bit when he mentioned reducing the amount of material and reducing the global warming potential of that material, right, by taking out the carbon or the cement from the mix. Health and wellness of the occupants is a priority as well, which we're going to talk about the mechanical system, which addresses that. And then finally, flexibility and adaptability, being able to use this system on a numerous types of buildings and provide flexibility for design. So here is a view of our prototype building. This prototype is showing a roughly 30,000 square foot floor plate, 8 stories tall, and it's built out of a kit of parts. The kit of parts include a thermally active floor system. We'll talk about what that means in a little bit. And also precast beams and precast columns, and a prefabricated lateral force resisting system. In this case, what is shown is a panelized coupled shear wall. And all of these components are manufactured off-site in our plant, and then trucked and to the site and assembled there. So let's take a closer look at the structural system to see how it all comes together. The thermally active floor system, which I mentioned previously, consists of 2 different panel types. There's a ribbed floor panel, we call it an RFP, and the solid slab panel, the SSP. The ribbed floor panel has 2 18-inch wide pre-stressed ribs that are 10 feet on center that support a 4.5-inch thick concrete mild reinforced flange, as John mentioned previously. The solid slab panel is 4.5 inches thick, and it spans between the ribs of adjacent rib floor panels. So we alternate the panels, rib floor plank, solid slab plank, and the SSP follows the contour of the rib to provide a flat floor, which is very important because what we're providing here is a pre-topped diaphragm. Pre-topped meaning there's no cast-in-place topping slab that goes over the top of the precast. And this is very helpful to our sustainability story because now instead of providing ready-mix concrete that you're not able to remove as much of the cement, very little in fact, where you have to put a 3.5, 4-inch topping slab, we don't have that now. We can use our low cement carbon shield mix in the plant thanks to our manufacturing process and significantly improve the sustainability. This is a very strong and stiff system. We're able to achieve long spans that are very helpful to the design and flexibility of an office building. Architects really like eliminating columns. The system can span 55 feet. That's very far for an office building. And we can do that with a 24-inch structural system depth with very low camber. So it's a very robust system. And if at locations where we have shorter spans, up to 36 feet, we can do that in 18 inches. Now, you'll notice that there's notches in the ribs of the RFP. If you look closely, those notches allow us to tuck the mechanical system, the ductwork, up into the structure. And that, combined with the smaller ducts, thanks to the mechanical system that we're going to talk about in just a minute, we're able to reduce the floor-to-floor height compared to a steel building by 2 feet. Now, that's a significant savings in skin cost, material cost, finishes in the building itself, and not just cost, but also material and carbon impact. So let's talk quickly about the integrated mechanical system. The key component of this is the in-slab radiant. The radiant PEX tubing is in multiple zones in the panel. There's an inner zone and an outer zone. They can be controlled independently from one another. So when you have that solar heat gain that occurs on the perimeter of the building that needs to be treated differently than the interior, you can control them separately. And that's a very important part of the way that this system functions. And I am going to skip over that quote, but basically we worked with Noah Zalen, from principal mechanical engineer with Integral Group, who was key to the development of this system to ensure that it works properly. And he's a big fan. All right, let's see. Integrated control solution. So the control system is also prefabricated in the plant in addition to the PEX. So there's sensors, controls, piping, and a backnet controller. They're all installed, tested, and calibrated in the facility. And so when it comes out to the site, it's already there. All you have to do is connect the hydronic piping to complete the system circuit. And here's a quick look at the section cut. You can see the ductwork is a quarter the size of conventional. Instead of pushing up to 1 CFM per square foot, we only need 0.2 to a quarter. You need to expose the ceiling, but you can have up to 60% or so coverage with ceiling, and acoustical treatment with cloud ceilings. And fans allow for personalized comfort for the occupants. Solar control is also very important because that eliminates or reduces the solar heat gain at the perimeter of the building.
All right, so all of this, what's really cool is this: we're taking this very bespoke system. Field constructed radiant construction is very time consuming out in the field, and we've managed to take it into our factory, and we're able to do it very efficiently, and we're able to deliver the savings back to the customer and basically give them this high-end, top-performing system. So, this chart here, I've got a couple things listed. So baseline, that would be like a gas boiler, basically, like not a very efficient system that maybe from 10 years ago. And then you're seeing the VRF is representative of an all-electric system that's in maybe modern construction. So that's total EUI, energy use intensity for a square foot. And then our system is all the way down at like 20 overall over the whole building. So the HVAC system itself is using about half the energy of a conventional, not conventional, but a pretty high-end all-electric system. And then on the embodied carbon side, again, comparing this back to a traditional office building in California market is typically built out of steel, concrete over metal deck. So we use that as our baseline, and then we compare it up against it, doing a whole life carbon analysis over a 60-year period. And we're saving about 40% of the carbon through the life of the building. And we're beating it in every category, basically: the structure, the skin, the energy use, the refrigerant, everything. So we're pretty excited about this. Just to give you, we don't want to leave you with everything theory, right? So we've been erecting this exact floor system that we were showing you is going up right now in the Napa Valley for a Calvet facility, skilled nursing facility. So this is just some pictures of that job site and just what we're doing out there. Here's some pictures of the floor system being flown in. Picture of the completed floor before we did the pour backs. So all these little troughs We fill those with concrete to stitch the whole system together and give it the seismic resistance it needs in California. And then just a few more pictures showing, a closer look at some of those troughs, and then also, the crews filling them in there. So yeah, this has been a fun journey, taking it all the way from concept to we're building it. So, thank you.